Hello. So, unfortunately I can't be here today, but I thought I'd record this lesson rather than just leaving work. Most of this is coming from page 248 onwards in the textbook. Okay, so if you want to have a look at that, that would be fine if you wanted to carry on and follow on with the text. So we're still building on the work that we did with combinatorics. Okay, so, and we're looking at different combinations and how many different ways we can arrange things. Now, to start with, this is a little bit of revision, but what we're looking at is what's known as factorials. Now, this is just a way of representing an equation. Now, the example on the screen right now is exactly what we did in the last lesson. We got 5 trophies in a school's trophy cabinet. How many different ways could they arrange the trophies in a straight line? Now, how many options are there in the first one? There's 5, and then there's only 4 left. 3 times 2 times 1. Okay, so that's how we represent this equation. And if I go right through this, I'd end up with 100. This would equal 120. Now, whenever we have this sequence of starting with a number at the top and then reducing as we go down, 5 to 4, 4 to 3, 3 to 2, what we can do is we can represent that like this. Okay? So what this means is if you start at 5 and you go all the way down to 1. So if I go down further, 3 factorial would be equal to 3 times 2 times 1. And in this case, it'd be 6. So that's the idea behind using that factorial notation. Okay? Now, what we can also do is that we can divide these. Now, I might actually do a simpler example to start with. If I said 4 factorial divided by 2 factorial, if I was to write this out in full, we'd end up with this divided by 2 times 1. Okay, now using our simplification, you got to look for the bits that are in both parts, and this 2 and 1 is also up there. Okay, so what that means is, is that cancels with that, which means 4 factorial divided by 2 factorial is equal to 4 times 3. Okay? Now, the hint on this is as follows. So I'll do 7 factorial divided by 4 factorial. What that means is this. Start at 7 and you keep going down until you reach the number that's 1 larger than the factorial represented in the denominator. Okay, so that would be that one there. So if I did, 13 factorial divided by 10 factorial, this would be equal to 13 times 12 times 11. So the top one tells you where to start, and the bottom one gives you one below where you've actually got to finish. So that's the shortcut for all of this bit here. So if I then go back to these examples, if I can work out how to scroll back up, if I was doing this one here, I might not do all the way, but I'd start at 18 times 17 times 16 times 15, and I'd go all the way down until I got to times 6, okay? And that would be the end of it, okay? So that's the key when it comes to factorial. For this bottom one, look, this is probably getting up towards some extension stuff because we're sort of trying to look at the mechanics of how this factorial works. But what we know, if I was to keep this in fraction form, is that, oops, it's n, not x. N minus 1 would be our starting point in the same way up here that 18 is our starting point. What would be the next number though? Well, if we look up here, what happens? From 18 to 17, it just goes and subtracts by 1. Then our next one will, oh, silly. Okay, so we are just reducing by 1. And I'll put the next one in too. Oh, why do I keep doing that? N minus 4. Now on the bottom, it's the same. We're still doing factorial. What would the next one be? Oh my goodness. 4 n minus 5. Now eventually, we don't know what these numbers are, but both of them will go down to 1. Okay? Now, if you look at these two, in the same way that we look for, where it's the same in the numerator and the denominator, you might be able to notice that from there, that direction is actually the same as that's there on the denominator. So, despite the fact that we actually don't know how many numbers there are or what n is, that can go and that can go. So in this particular case, our answer would just be n minus 1 times n minus 2. Again, look, this is probably, if you struggled with that part B there, don't stress out too much. It's probably starting to get up into the more challenging areas. But it's just about cancelling out the fractions and just trying to understand how the mechanics of these factorials work. Essentially, you have a chain of numbers that keep reducing by 1. And it doesn't matter what those numbers are, that's your starting point and that's how far you go. Okay. Now, so what we've got, that brings us on to what's known as our permutation rule. Now, permutation is not a word we've used, but it's just another way of saying an arrangement. Okay, so this, I know that we've used a few new terms in the last couple of days, but this is permutation rule is how many different ways can we arrange things. Okay, now, so make sure you get that rule down, and then I'll most definitely do an example. Now, the example is this. Let's say we've got a netball club of which 7 people volunteered for the committee. All 7 are happy to be president, secretary, or treasurer. Okay. Now, this here tells us that there are 3 positions. Now, this is not too different to the work we did before, okay? We've got 7 things to choose from. How many different ways could we arrange 3 people to do these jobs? Okay, this is look back on the work that we did the other day on Monday. It's exactly the same. We've got 7 people, and how many different combinations could there be for president, secretary, and treasurer? Now, I'm going to rewrite this using this correct notation using the rule. And the way it would be is like this. n total people. I'll say people. It might not be people other. How many choices? So I'd rewrite it like this: 7p3. So there are 7 volunteers. How many different ways can we arrange it? 3 of them. Okay. Now, again, looking up, remember that this 7 is n, and looking up here, the way we do this is 7 factorial over n minus r factorial. Which could then be simplified to 7 factorial divided by 4 factorial, which tells us that we can do 7 times 6 times 5. Okay? Which is the same logic that we did. We're just expressing this in a better way. Okay? So that example's on page 251 if you needed further guidance, or you want to rearrange that or rewrite that, I suppose, in more detail. Okay, now the very last thing I just want to cover is what's known as arrangements in a circle. At the moment, we've put 4 things in a row, okay? But when it's in a circle, it just changes the dynamic a little bit, because at the moment, this one is not next to this one. But if they're in a circle, such as over here, the first and the last actually become next to each other. Now, this example of a table that's got 4 seats, and we've got 4 different people. Oh, sorry, how many different, so the question is, how many different ways could 7 people be seated 4 at a time around this table? Okay, so it could be 1, 2, 3, 4. Person 1, 2, 3, and 4. But that would be different from 1, 2, 3, and 5, which would be different from 1, 2, 3, and 6. But that's also different from 1, 2, 5, and 6. Okay, so there are a lot of combinations. So you don't necessarily have to fully understand how this rule is developed, just an understanding that it's different from a straight line. We're talking about joining on the edges. Now, the good news is there is a formula that is similar, and it is as follows. So that's the rule. Now, we already know this top bit because that was part of the previous rule. So it's like you work it out as normal, as though it was in a straight line, and then divide by r, right? So that's how we go about this one. So let's rewrite this one properly. So 7p4 divided by 4. Okay, so that's the first step. Next, 7 factorial divided by 7 minus 4 factorial all over 4. Okay? Now the top can be then represented as, remember that this equals 3 factorial. I'd go 7 times 6 times 5 times 4 divided by 4. And if I crunched all this out, I'd end up with 210. Okay? So that's the arrangements in a circle. What I would like you guys to do for the remainder of this lesson, 253, 23b. There are a whole bunch of examples. You guys got to work through those. Just look for the bit where it says worked examples, and you should, so the worked examples, it sort of says it with a little arrow thing like that. Just look, then flick back through the textbook and you see work examples that are similar that will hopefully help you along the way. Okay, good luck.